Hello, and welcome to Wireless Design. Wireless network connectivity may be one of the most influential and widespread technologies of modern networks. Even though it's what I feel is one of the least understood technology areas of network engineers today. Most of us are familiar with the practical aspects of setting up an SSID and setting a password, but nearly all network engineers I meet have only a vague familiarity with enterprise wireless design. Before we get into the Cisco wireless design practices, let's do a brief overview of wireless technologies. So in the last 20 years, wireless standards have come quite a long way. Back in 1999, IEEE released the 802.11a wireless standard. This had a maximum theoretical throughput of 54 megabits and operated in the 5 gigahertz spectrum of frequencies. That is to say, it used the UNII bands here in the United States. That's the unlicensed National Information Infrastructure. At a 40 megahertz wide band, this allows for 12 non-overlapping frequencies. In the same year, IEEE also published the 802.11b standard that offered lower throughput at 11 megabits, though it operated in the 2.4 gigahertz spectrum. That's the ISM band, or the Industrial, Scientific, Medical radio bands. This may have offered lower throughput, however, it had a feature of being able to reach farther and have better physical penetration through walls and other obstructions to line of sight. So it was a bit of a trade-off, right? You get lower speeds, but you can be further away from the access point and have more stuff between you and the access point and still have good signal. The ISM band at 22 megahertz wide channels offers 3 non-overlapping frequencies. These are often referred to as channels. In the graph at the bottom here, we see where each channel resides in the ISM band. The 3 channels at the top, 1, 6, and 11, here, here, and here, are the primary channels that do not overlap. Of course, you can use 2, 7, and 12, or 3, 8, and 13 that you see, here and here and here, and it looks like those don't overlap. But because the top 3, 1, 6, and 11, that their usage is so ubiquitous, it's recommended that you use those so you're not overlapping with everyone around you who may be broadcasting as well, and this will provide the best wireless signal that you can get. You can see that IEEE has steadily improved wireless communication, with 802.11ac giving throughput of 2.3 gigabits and operating in the 5 gigahertz band. The most recent standard released, and I'm talking here in the middle of 2019, is 802.11ax, which is set to replace 802.11n and AC. This new standard changes the game a bit and boasts theoretical speeds of up to 11 gigabits. For the exam, certainly know the standards here in this table, what band they operate on, and the non-overlapping channels. Moving on through our wireless overview, let's talk briefly about what an SSID is, or a service set identifier. Almost everyone knows this as the name of the wireless network that's broadcast. This equates to a VLAN on a wired network. All devices communicating on a wireless network must have the same SSID configured. Cisco recommends mapping each SSID to a separate VLAN, as typically your different SSIDs will have different security requirements, and it makes little sense to have the same VLAN accessible by a higher and lower security wireless network. The SSID can be 2 to 32 characters long, and at layer 2, you may not realize that wireless works with carrier sense multiple access collision avoidance. And what's this? Half duplex. When using the air or space as the transmission medium, there's no way to detect a collision or operate at full duplex. A client or access point both listen first before transmitting to see if anyone else is transmitting. If they are, it waits for a random backoff timer, then tries again, and continues trying until it sees an opening to transmit in. This is why when someone says they're having trouble because the wireless in the area is crowded, it's actually because one side or the other is having to wait a long time to find an opening where it is able to transmit. And this just applies to the channel that the SSID is operating on. So that's why you would want to use 1, 6, or 11 so that you don't end up getting, overlap and having it there. If you use channel 2, then you might have to wait for devices that are transmitting in 1 and 6 to go ahead and stop transmitting before you can transmit. So now we've had a brief overview of wireless, let's go into Cisco's wireless design recommendations and framework. Cisco created the framework of the Unified Wireless Network. The Unified Wireless Network contains wireless clients, access points they connect to, unification of the wired and wireless networks, management of the wireless networks, and mobility services to allow users to roam when wireless. The bottom 3 elements here are provided by the Cisco Wireless LAN controller. These, which will go into some detail about the controller and its operation shortly here. Cisco is clear about the benefits of using the Unified Wireless Network framework, and they are reduced total cost of ownership, enhanced visibility and control of the wireless networks, dynamic radio frequency management, wireless LAN security, unified wired and wireless networks, enterprise mobility, which enhances productivity and collaboration because staff are able to work wirelessly within the corporate campus. And the Unified Wireless Network requires a centralized design. Most people are used to their wireless routers or a wireless access point you purchase and configure individually, but this simply does not scale. And there's a fair number of features that are lost by the access points not operating as a single wireless network. In the centralized design, we use lightweight access points, or LAPs. You might hear it pronounced LAPs. These access points are controlled by the Wireless LAN Controller, or WLC. The access points are generally not operational independently. They have enough brain power to be able to boot up and look for a wireless controller, and that's about it. They need to be told how to do anything and everything else. The diagram here illustrates a CAPWAP tunnel. In most deployments, the end user traffic does not actually enter the network at the access point. Rather, the traffic is tunneled through the network to the wireless controller, and then terminates into the network and enters the network at the physical port where the wireless controller connects in. This is beneficial for a number of reasons. Among them are that we do not require end-to-end VLANs. The VLAN to which your SSID is mapped only needs to exist up to where the wireless controller is located and does not and should not exist where your access points connect to the network. This provides improved security and really facilitates a better design overall. At first, Cisco access points in a centralized design used the Lightweight Access Point Protocol, or LWAP, to communicate and transport user data. This was a Cisco proprietary protocol and used AES, or Advanced Encryption Standard, for data encryption. It uses UDP 12.222 and 12.223 for control messages and data transport respectively. The industry standard response to this is CAPWAP, or Control and Provisioning of Wireless Access Points. CAPWAP is now the preferred protocol for both Cisco and non-Cisco lightweight access point communications. This uses DTLS for encryption and UDP 5246 and 5247 for control and data, respectively. When I mentioned that user data is tunneled back to the wireless controller for entry to the network, it's an LWAP or CAPWAP tunnel that's being used to transport that data. These protocols are also responsible for the discovery process and provisioning control messages that are sent between the wireless controller and the access points. Overall, you don't need to be concerned with the details of how the protocols work. However, I would commit the information on this slide to memory. Now, your design may be configured in such a way that you don't want your user data to be transported back to the wireless controller for entry to the network. Perhaps bandwidth over a WAN link to one of your branch offices is rather limited, and you want the user's internet-bound traffic to use the ISP connection at the local branch office, rather than use the WAN link and go out the internet from the HQ. This is where the concept of split MAC versus local MAC operation comes in. In split MAC operation, the wireless controller is the termination point where the client data enters and exits the wired network. In local MAC operation, however, the client data terminates at the access point. The wireless controller in this circumstance still handles a significant portion of the operations for things such as association and disassociation requests and authentication. So this slide shows the modes that an access point can be operated in. Local mode is the default and normal operating mode you'd expect to see an access point in, of handling user data traffic and broadcasting SSIDs. However, HREAP, or Hybrid Remote Edge Access Point, is a mode used for managing lightweight access points over a WAN. This allows for local MAC or split MAC operation. REAP mode can allow for the wireless at a branch office to remain functional in the event that the WAN link is lost. So the lightweight access point has some autonomous capability while it has lost connectivity to the wireless controller in this mode. With monitor mode, the access point is just listening to provide location-based services. In rogue detector mode, the access point is also not participating in handling user traffic, and instead it's only listening for surrounding access points. The AP collects the broadcast MACs of each of the access points it can hear, and it sends them to the wireless controller. So the wireless controller can determine if any of them are seen on the wired network. And if they are, then in that case we know that there is an unauthorized wireless access into the wired network. In sniffer mode, the access point is capturing all traffic on a channel. This is only supported with Cisco when using the application called AeroPeak. Finally, the lightweight access points can be operated in bridge mode, which provides a point-to-point or point-to-multipoint wireless bridge to perhaps connect two buildings or connect a remote location where running a wired connection was not feasible or was impractical. For the exam, certainly be familiar with what modes exist and what they're used for, although you shouldn't need to be familiar with any details on their operation or configuration. When a lightweight access point first boots up, it'll go through the process at the top here. First, it'll try to discover the wireless controller using CAPWAP. If that doesn't succeed after 60 seconds, then it'll try LWAP. After another 60 seconds of using LWAP, if it can't find the wireless controller, it'll go back to using CAPWAP and then try again and repeat this until it locates a wireless controller. Once the wireless controllers are located, if it has multiple to choose from, it'll select which to associate with using the below order. You can manually configure a primary, secondary, and tertiary wireless controller for the access point to associate with, which you'll see when we discuss redundancy design shortly. This will be your primary method of defining your redundancy method. If you have not manually configured any wireless controllers, then the access point will associate with the wireless controller, which is configured as the master. In the event the master is not available, it'll associate with the wireless controller that has the greatest capacity available, which may not be the one with the least associations, depending on the models of wireless controllers in your network, and you'll see shortly that different models have different number of supported access points, and whichever controller has the greatest capacity for additional associations is the one that would be selected here. The wireless controllers themselves have three main components: WLANs, interfaces, and ports. The WLANs are identified by an SSID and are assigned to use an interface. The interfaces are logical connections which map to a VLAN on the wired network, and there's 5 different types of interfaces, 3 of which are mandatory to be configured. The management interface is for in-band management and is one of the ones that are mandatory and must be configured. The service port is for out-of-band management, and that's actually optional, and honestly I rarely see this one configured. That typically people go for in-band management. The AP manager interface is used for AP communications, provisioning, and association, and is also a mandatory interface. The dynamic interface type is created dynamically and are the interfaces associated with SSIDs for user data traffic. The virtual interface type is used for DHCP relay traffic and authentication traffic, like Radius or .1x. Finally, the ports of a WLC are the physical ports which connect to the wired network that the logical interfaces use for communication. Now, Cisco has many different models of wireless controllers out there for a variety of different use cases. They each generally have a different number of access point associations they can support per physical port. This table here gives a brief overview of some of the models available for wireless controllers. You can see here that we even have a wireless controller module for our ISR, or one that can be inserted to our chassis-based switch. For the exam, certainly ensure you're familiar with the models here and the number of access points that are supported. Now, one of the major benefits of having a centralized wireless design and the unified wireless network is the ability for automatic radio resource management. Now, what do I mean here? I mean that when you have wireless access points everywhere, to ensure you have coverage in the places you need most, you also end up with a lot of coverage overlap. This can cause access points to interfere with one another and cause more problems than you solved by placing more access points. An individual wireless controller can automatically manage the transmission power and channel selection of the lightweight access points to ensure you get as minimal interference as possible while maintaining maximum coverage. However, you can imagine this could cause some problems if you have a design that ends up requiring more than one wireless controller. This is where RF groups come in. Access points send neighbor messages all the time. When an access point hears a neighbor message that it registers at least minus 80 decibels, where dBm is just the unit of measure for wireless signal, then a neighbor relationship is formed as long as the wireless controllers have the same group password configured. When wireless controllers form an RF group, they elect a master, and the master controller is responsible for doing the calculations for the radio resource management to coordinate all of the access points in the group so they don't interfere with each other, or at least have as little interference as possible. And having multiple wireless controllers leads me into the next slide of wireless LAN redundancy. There's two methods you can take to wireless controller redundancy design, and that's deterministic and dynamic. Basically, this means that you can either plan out and manually configure what wireless controller each access point will associate with to begin with and what controller they'll fail over to in the event that their primary fails. Or you can just hook it all up and leave it to the algorithms to decide what happens. If you're dealing with a campus with hundreds or thousands of access points, you may be tempted to go with the dynamic design, but this is simply not a good idea. Cisco recognizes that there can be significant time saved, and there is less complexity in the configuration. But you trade this off for less predictability in the wireless network's behavior, less stability in the wireless network overall, and slower failover times when the access points need to decide for themselves what wireless controller to fail over to, rather than having a backup pre-configured. The key takeaway here should certainly be to use deterministic design, not dynamic. And moving into our last couple slides here, let's talk briefly about how to handle wireless designs at the branch office. As I mentioned briefly before, REAP and HREAP, that's Remote Edge Access Point and Hybrid Remote Edge Access Point, still control the lightweight access point with a controller, but they allow for local MAC operation, making it so user data doesn't need to traverse a WAN link to the wireless controller, but rather terminates into the wired network at the access point. This can allow for wireless networks to remain operational in the event of a WAN link failure. Below, we have some of the wireless controller options that Cisco recommends for the branch office. I'd be familiar with these and the number of access points supported by each. And finally, let's go over a couple considerations for your wireless design. In the table, I just have an overview of the port numbers used for communications that are associated with the wireless network. RF group communications, wireless controller exchanges, CAP-WAP, and LWAP. The bullets at the top here, make sure you commit these to memory. Cisco's best practice for wireless networks are to limit each access point to no more than 30 devices per SSID. This can be tough, and you may need to place additional access points in areas of high traffic, like conference rooms or classrooms. For voice over WLAN or VOWLAN, limit it to 7 G.711 calls or 8 G.729 calls per access point at any given time to ensure you maintain acceptable call quality. You may not know what these are yet, but G.711 and G.729 are voice codecs, which we'll cover later in the series when we go over voice and collaboration design. Finally, if you're doing voice calls over the wireless, ensure you have QoS enabled through the wireless network, and at the Cisco's best practice recommendation, use the Platinum QoS profile on the wireless controller. So in the wireless controller interface and in the command line, you actually have the ability to set a QoS profile. You would use the Platinum profile if you're doing voice over WLAN. Phew, I know this one was a bit intense, but thanks for hanging in there with me. As before, let's go into a couple practice questions before we wrap up here. Now, which wireless controller interface is dedicated for wireless LAN client data? We'll just go through these briefly. The virtual interface is the one that's used for DHCP relay and authentication traffic. Your service port is used for out-of-band management, and AP Manager interface is used for your AP associations and control messages. So the dynamic interface is the one that's actually used for your client data. So that would be B. And finally, based on best practices, which QoS profile should be configured on the WLAN of the wireless controller for wireless VoIP communications? I know we just spoke about this in the previous slide, but I really wanted to drive this one home, that you would use the Platinum wireless controller or Platinum QoS profile on the wireless controller. I've seen this pop up on the exams before, and you'll definitely want to be sure that you remember this one. Now, I hope this has been informative for you, and I would like to thank you for viewing.